Hello everyone, my name is Gaurang Gupta and today we will be doing another machine learning project which is plants classification. In this what we have to do is we have to make a model, or you can say a deep neural network model or a convolutional neural network model to predict what the image is. What I mean by this is, here you can see in, wait a minute, in training folder we are given with some folders like aloe vera, banana, cassava, coconut, corn, etc. We have, and each of these folders contain images. We have to train a model on these images so that it can predict the images from this test set and then this validation set. So here you can see we have multiple classes. That's why it is a problem of multi-class classification. In this, it is also given that each one of the classes has almost 100 files, means 100 images. So let's see one of these folders. So aloe vera. Here we have images of aloe vera plant. Now you can see that each aloe vera plant image is of different size. Here you can see it is 6.88 kb, 12.05 kb. So we have to make these images of same size. We can't just say that okay, we have different size images, let's just directly feed into our model. No, have to rescale them, and it is a pretty simple process. These libraries which we are going to use, the models which we are going to make it very simple. So let's start coding. First, we will import all the necessary libraries. We will import NumPy, not NumPy as NP, import TensorFlow as TF, from TensorFlow, import Keras, from, from Keras, import layers and models, from Keras dot preprocessing dot image, import image data generator, import matplotlib.pyplot as plt, from keras.applications import Inception, ResNet p2, densnet 201, densnet 201, and ResNet 152. ResNet 152. What are these models? These are pre-trained models provided by Keras. What happens is that to achieve more accuracy, or you can say to achieve more accuracy in less time, what we do is we use pre-trained models. These are some examples of pre-trained models. Keras give many pre-trained models. You can check them. I have selected these three. So first run it, and let me add it here. While it is running, let's move on to image processing. Now, image pre-processing here is somewhat different. What happens is that we will use this image data generator. It scales the images. It also applies all the necessary things we want to apply to an image before feeding it to our neural network. So for this, first we will define a function def train val generators training dir testing dir testing dir, and lastly validation dir. Then train data gen, it will be equal to image data generator. Then rescale, we have to rescale these images, 1 point divided by 255. Then rotation angle, that will be 180. This rotation angle value can vary from 0 to 180. So you can use any value between 0 and 180. It is in degrees, not in radians. Then width shift range. That will be 0.2, means 20%, not 0 and 2. Right, do 0.2. And then height shift range is also 0.2. Then shear range also 0.2. You can change these values, but these values should remain from 0 to 1. Zoom range, that will also be 0.2. Then horizontal flip, that will be true. And fill mode will be nearest. Now, what are these parameters I passed? Rescale value just rescale the images. The rotation angle, we rotate the images randomly through random angles. This is done to make the images large, or you can say number of images large. That we need bigger data sets, so we use these parameters. This process is called image augmentation. Then we will use train generator, not generatory, generator, train data gen dot from, not from, flow from directory. Then directory will be the training dir. Then class mode will be categorical, and target size will be 100 cross 100, 100 comma 100. So it will scale every image that is passed through this training data generator with this target size. You can change this target size, but keep a reasonable target size, because if the target size is large, means the image is large, it will take some time to train that. So do it accordingly. Now for test data gen, that will be image data generator rescale. This rescale parameter is, you can say, common, and you have to apply this no matter what, for whatever data set you are using. These values, these are the image augmentation values, and it is suggested only to use it for the training data gen, or training data. So test generator will be test data gen dot flow from directory will be testing dir. Class mode again categorical, and target size will be 100 cross 100. Now same for validation, to image data generator scale will be 1 plus, and validation generator will be, copy this, then change this test data gen to validation data gen. And lastly, we will export all the generators. So return train generator test generator, and then validation generator on it. And then we will use this function. Scroll it down a bit, and then training will be equal to slash kaggle slash input slash plants classification, and then train. Copy it, then test, and let's rename it to testing, and then validation, and val. Then copy these, paste here, and use this function. What was the function name? Train val generators. Train val generators. And pass all these paths which we just wrote here. And validation. Run it, and we got an error. What is the error? Here the rotation angle is there. Let me check it. Error here is the rotation angle. I have to put rotation range. The parameter is rotation range, not rotation angle. So keep that in mind. Run this and then this. So here you can see this message is the confirmation that our code ran correctly. That it has found 21,000 images which belong to 30 classes in this training, 6,000 images for testing, and then another 6,000 images for validation. So now let's move on to image visualization. Now for image visualization, first we will make an array or a list with the xtrain, and then c will be 0 for feature comma label in train generator xtrain dot append np dot array feature, and then c plus equal to 1 if c is equal 1 break. I will tell the reason why I wrote this code that way. So xtrain will be np dot array xtrain, then print xtrain dot shape, then xtrain will be equal to np dot reshape xtrain, and we have to assign the shape of 32 100 3. Then print xtrain dot shape. Okay. Run it. uh, abs, why it is abs array I used? So np dot array, not abs array. See, what happens is that these generators make images in a batch. They convert these all images into batches. So there you can define batch here. It is a parameter called batch size which you can define. It can be 1 to any number of images. There is no limit. But define that accordingly, because sometimes the performance of a model highly depends on these parameters. So the default value of this batch size is 32. Remember that. Here also you can see we got the value 32. So we have to reshape that into this so that we can easily plot those images. Now we will plot those images which we just stored in this xtrain variable. For this, fig comma ax will be plt dot subplots 4 comma 4 comma fig size, not font, fig size will be 30 comma 30. Then for I in range 0 to 16, ax int I by 4 comma I mod 4 dot im show xtrain I. Run it. So now our code is executed. Here you can see we have images from a training generator. What you can see also here is that images are skewed. Some images are rotated, some you can say here there is some blur, and in these images are also blur. This happens because we are doing image augmentation. It sometimes breaks the images, so when we rescale them, when we plot them, it do that, but It's actually good because it makes our model more robust. We can't train the model on all the images taken in the world. It should know that there are some images we are never going to find, and still our model should behave correctly and should behave efficiently. So for that case, this is helpful. Now let's move on to model creation. So for model creation, we will first define a function def create model, then models dot sequential, then layers dot conv 2d 32 comma 2 comma 2, then activation function will be relu, and then input shape will be 100 comma 100 comma 3. Here 3 is the color channel and 100 comma 100 from this target size. So whatever the target size here, you should use the exact same here. Here, then layers dot max pooling 2d 2 comma 2, then copy these, control C, control V, change this 32 to 64, then again copy it 64 and change it to 3 comma 3, copy it, paste it, then layers dot flatten, then layers dot dropout 0.1, then layers dot dense 512, activation again will be relu, and then layers dot dense dropout 0.1, then layers dot dense will be 30, and activation is softmax. Now these layers, these dense and dropout layers, dense layers are actual neurons, actual blocks which act as a neuron, and dropout is that we are dropping some of them out. It happens that sometimes we overtrain, which is also bad for accuracy. We don't get the accurate model. So to stop or to counter that overtrain, we use this layer dot dropout. And here the dense function has 30. This 30 came from here, number of classes. It should not be different because then it will throw some errors. Then model dot compile optimizer will be Adam, loss will be categorical cross entropy. If you are using only two classes, if you have only two classes, then you can also use binary cross entropy in place of categorical cross entropy. And metrics will be accuracy. Then return model. Run it. Now we will train the model. So model will be equal to create model, then epochs will be 10, and then history will be model.fit train generator, epochs will be epochs, verbose will be 1, validation data will be test generator. Run it. The code is running and it is taking some time. So let's move on to next section, which is plotting, training, and testing accuracies. For this, first we will define a function which is def plot accuracies, history, Then ACC will be history dot history, accuracy. Then val accuracy will be history dot history, val accuracy. Then loss will be history dot history, loss, and val loss will be history dot history, val loss. Then epochs will be range, length, accuracy. Then plt dot plot epochs, accuracy, red, plt dot plot epochs, val accuracy, comma blue. Then plt dot title training and testing accuracy, and plot plt dot x label. Here also, this will be plt, not plot. Plt dot x label epochs. Then plt dot y label will be accuracy. Then plt dot legend, legend. Then plt dot show, and also a new line. Now plt dot plot epochs, comma loss, comma r, plt dot plot epochs, comma val loss, comma blue, plt dot title training, and testing loss. Then plt dot x label will be epochs, plt dot y label will be loss, plt dot legend training, comma testing, then plt dot show. Also in here we have to copy this, paste here, and run it. Now use these functions, plot accuracies, and pass the history object. Now let's code the final section, which is using Keras inbuilt models. For this, first we will use a variable pre-trained models equal to a list with models. Inception ResNet v2 will be include top will be false because we will define our own top value, false. Then input shape will be 100 comma 100 comma 3. Then pooling will be max, wait a minute, pooling will be max. Then classes will be 30, weights will be of ImageNet, and classifier activation will be softmax. Then densenet include top, rain false, input shape will be 100 comma 100 comma 3. And then all of these are same, so I'm copying it. And then last model which is ResNet, and it will have same parameters. Copy these and paste here. Then we will define a new list which is final models. It is empty for now. Then for model in pre-trained models, trained models, for layer in model dot layers, layer dot trainable equal to false. It means that the pre-trained models will not be retrained and their values will be preserved. Then m equal to models dot sequential. Then m dot add model. Then m dot add layers dot flatten. Then m dot add layers dot dense 512. Activation will be relu. Then again m dot add layers dot dense, layers dot dense 30 comma activation will be softmax. Then final models dot append m. Run it. Then for each model in final models, we'll print the model summary. Model dot summary. Then for each model present in the final models, we will compile each one of them. Compile optimizer. Optimizer will be Adam. Then loss again will be categorical cross entropy. Categorical cross entropy. Then metrics will be accuracy. Accuracy. Run it. And then for each model, again in final models, history will be equal to model dot fit train generator epochs will be 10, epochs will be 10, verbose will be 1, verbose will be 1, and validation data will be test generator. Then plot accuracies, and then pass the parameter history. Run it. So now our code is executed completely. Here you can see, let me show you the first one. Here is our model which we built from scratch. You can see we have an accuracy of 45% on training dataset and 46% on testing dataset. And you can also see by graphs, let me show you here. The accuracy is rising almost in a smooth way. There is no jerks. In testing dataset, there are some jerks that accuracy is increasing rapidly. Sometimes it is increasing slowly, but that's okay. And in training, there is very smooth line, so it is good. It says that if we have trained for more epochs, it would have been more accurate. But again, time is a constraint for us. Then you can see the loss. Same story with the loss. Then when we used built models of Keras, here are the model summaries, so you can check them. And then the models. So first model 51% training accuracy and 58% validation or testing accuracy. So even if we have trained this model for more epochs w- without any say fine tuning, it would have been close to that. It would just be a time waste. With the losses, there is the same story. Here you can see some jerks are there, but the accuracy is rising. This model needs fine tuning, and it can perform very well if we have trained for more epochs, and also some fine tuning if we have done. Here you can see accuracy is showing that 72.63% training accuracy and 74% validation accuracy. Now this model, this is the loss, sorry. So loss is also showing the same story. Now here, this model, you can see that validation accuracy is freezed. For 10 epochs, it hasn't changed even a single bit. And testing, and you can say training accuracy, it's like peaks and valleys. There is no conclusive evidence. Same with the losses. So this is the model which is the worst. So you, even if we apply all the fine tuning, it might not perform well for this particular data set. I'm not saying this model is bad, but this model is bad for this particular data set. It can happen that this situation can occur in this model. So remember this, these models, when we apply them to a dataset, depends on the dataset that what accuracy you will get with what model. It is highly data dependent. Remember that no model is best, no model is worst. So our project is complete for now. So thank you very much for watching the video. If you like this video, do like, share and subscribe to my channel. If you have any doubts, do comment in the comment section. I would love to solve them. So thank you very much for watching the video. Thank you.